Okay. Um, at this point, actually, we are done with what I consider to be the foundational level study of continuum mechanics. Okay. There is more to be done, and there is, of course, much more that can be done, but it's worth, at this point, taking a break. And actually, in this entire segment, I'd like to sort of recap on what we've talked about. Not so much as giving you a summary, because that will take too long, but instead, I want to put things a little bit in context, okay? And perhaps the first thing to do is to do credits, okay? And this is not exactly what you may think of credits as, but what I want to do is to make the point here that really continuum mechanics is probably the, along with astronomy, is probably the oldest of the sciences, okay? It's exceedingly mature, okay? It comes straight down to us from at least Newton, and of course it could be traced further back before Newton, okay? From Newton, it went on to Euler. Around the same time, Euler and Lagrange, because Lagrange was a student of Euler. Okay? And then the development was taken over by, it was also taken over by Cauchy, and we've seen that the idea of stress is due to him. Others got into the act along the way, and I'm not claiming to be accurate with chronology here, but as we've seen that a whole bunch of other people got into the picture at this around this time. Samenow got into it. Okay, Kirchhoff, of course. Okay, the Italians, Piola. I should mention that some people take great offense when Piola is when Kirchhoff's name is associated with Piola's in the definition of two of our stresses. There are people who prefer that the stresses be ascribed only to Piola. Anyway, who else? Let's see. So Samenow, Kirchhoff, Piola. And then it came down to, of course, well, Young got into it in some way, but not in a significant way for the sort of treatment that we have given here. But then, so then it came down. There were others who did things, but we haven't really referred to some of those developments. The form of continuum mechanics that was presented in this series of lectures, that has been presented and will actually continue to be presented even after this segment, was truly developed in the period of the 1940s through about 1970, and there were developments after that as well. And then this came down to the school of what was called the rational mechanics. Okay, so-called rational mechanicians. And this was in the period of 1940 to about 1970, when the important developments were largely done. There were still some outstanding problems, and there remain some problems. But this is an important school. So of the school of rational mechanicians, there are a number of names, and I'll just list some of them. Most prominent among them, and not necessarily the ones who did made the most significant contributions, but definitely among the most prominent are Trustel, Knoll, Rivlin, Ericsson, let me see, Trusel, Knoll, Rivlin, Ericsson, of course, Tuppen. And this is not meant to be in order, okay? Mindlin, Pipkin, Coleman, and well, last but not least, there are others I'm definitely missing, and I'm sure when some people see this, they will take great offense. But Girton. Okay, and there are others. So, right. So these are the ones I've bracketed here are the members of the School of Rational Mechanics. Okay, and they are most responsible for laying down continuum mechanics as a rigorous mathematical subject. Okay. All right. So that's that for as far as credits go. The other thing I wanted to mention, and which I've probably been amiss in not talking about, is books. Okay. All right. There are a number of books on continuum mechanics. Again, I will list them by authors, and in some cases, I do remember the titles, so I'll list those titles. As you may imagine, many of the titles are some variation of the words continuum mechanics. Okay, all right. Books. So there are two books that are considered, I don't know, almost the holy books of this business. So the religion doesn't come into this, of course. But really, the most important books, the books that really have pretty much everything, okay, are two of them. The first is called Classical Field Theories. Okay, and this book is actually volume 3 of a series which is called Handbuch der Physik, or Handbook or Handbook of Physics. Okay. Now, this particular volume, volume 3, was written by Truesdell and Turpin. Okay, and the Handbook of Physics was edited by Wilhelm Flügger. And actually, Wilhelm Flügger's name should be added to the rational mechanicians. Okay, so let me do that. Okay, so that's one. The other is called, and this book is even more famous. It's Nonlinear Field Theories. Okay, and this is volume 4 of the same series. Okay, this volume is written also by Truesdell and Knoll. Okay, also edited by Wilhelm Flügger, of course. Okay, so these two books really contain pretty much everything. They're not easy reads. Okay, nor are they short reads. Okay, if you decide to embark upon them, it's going to take you many years. Okay. The ideal way to approach these two books is really to have particular topics of interest and go in there and learn about them. All right, so there are those two books. Continuing along the same line, a little more readable, a little more accessible. These books are accessible. It's not that they're not accessible, but a little more accessible is a book that now, I mean, its name is some variation, its title is some variation of the words continuum mechanics, okay? And this is by Mort Curtin. This book is a little more terse. Girton, at least in this version of the book, makes scant use of coordinate notation. Okay, so that makes the book a little terse, but it's a very good book. It's a classic. Another classic, a very slim edition is again some version of continuum mechanics, right, in the title. And this is by, I think, P. Chadwick. It's the initial, I'm not sure about the name, I know Chadwick is right. This book is available in Dover. Okay, so it's relatively inexpensive. Okay, so these 4 books that I've listed are justifiably considered the classics. There are many others, of course. There's one book which is actually a classic in its own right. It is called, if I'm not mistaken, it's called Mathematical Foundations of Elasticity. Okay. It's by Marsden and Hughes. This book, as the title indicates, is about elasticity, so solids. The first 4 books do treat fluids in equal measure. So this book is a very hard read. Okay? It requires you to have a background in real analysis and understand some amount of theory of manifolds, gets into differential geometry. It's, however, a very rewarding read because it sets you on the path to understand things like the continuum theory of defects. And so this book involves a lot of real analysis. Manifolds, theory of manifolds, it involves differential geometry. Okay. What's really nice, though, is that the background that it requires, and more importantly, what it develops in differential geometry is also one of the first, one of the many stepping stones that you could adopt to get into topics like relativity. Okay? So it can be quite rewarding. Finally, a much more modern book, a more recently published book, and really very accessible, which also and which also follows the same notation that I used here, is called Nonlinear Solid Mechanics. Okay. Also, as the title indicates, it's about solids and elasticity and related models. And this is by Gerhard Holzapfel. It's much more modern. There are many other books. Okay. Right. But these are the ones that I would recommend. Okay, so much for books. All right, next thing, let's talk about what lies beyond this now. Okay, like I said, what we've accomplished in the lectures so far is the foundational material that I have found useful in order to understand the mechanics of continuum bodies, fluids and solids and rigid bodies. There is much that can be done from here. One thing that one can do is to now extend this, and of course one can study everything about fluids from here, right? So you could go off into fluids and really study, you could go on to studying problems involving turbulence, laminar flows, of course. You could look at multi-phase flows, right? With this background, of course, there's more to be done if you want to do multi-phase flows. You could do what are called non-Newtonian fluids. Right, and understand more about them. Okay, we refer to non-Newtonian fluids when we were developing constitutive relations for fluids. You could also go on and study what are called complex fluids, right? Something I often mention is that we tend to think of fluids as isotropic, right? And that's not necessarily the case. There are fluids which have so-called directors in them and which are not isotropic. An example, by the way, are liquid crystal displays, right? Those are not isotropic. So there are all these types of topics that can be studied, right? And especially the study of non-Newtonian fluids and complex fluids does require the treatment of continuum mechanics that we've developed. In the case of turbulence, all of this is assumed, and so people tend to move on beyond that. With multi-phase flows, it can be a mixture. Okay. In the context of solids, there are things that you can do. You could, of course, just study linearized elasticity. Okay. The study of linearized elasticity, like the study of turbulence, assumes a great deal of this material, and often the treatments almost seem to forget some of this material. Okay. They tend to be much more focused on actually obtaining solutions to boundary value problems. So you could do that. You could also study other types of material behavior. You could study plasticity. Okay, you could go on to doing viscoelasticity. Okay, now the study of plasticity and viscoelasticity. And by these I mean studying these problems. These problems can be studied with infinitesimal or finite strains, right? And the theory is well developed for both. Right, and there are other sort of models. Within linearized elasticity, I would also include the study of fracture mechanics, right, of linear elastic fracture mechanics. Fracture mechanics of nonlinear elasticity is a little harder to develop. So there are all these kinds of topics that one can study. One can go on then, and this is what we will be doing, which is going on to studying other aspects of continuum physics. Okay. So not necessarily mechanics alone, but one could study thermal physics, I guess. Right? Thermal physics is often tends to be thought of as something involving a lot of statistical mechanics and so forth. But when I use it here, I mean continuum thermal physics, right? So in particular, one of the things that we are going to be doing with the next segment, starting with the next segment, is looking briefly at how problems of thermomechanics are formulated, okay, from the basis that we've developed here. Okay, The other aspect that I will do a little bit of is mass transport, as I said at the very beginning of this series of lectures. Okay, so all of these are sort of formulationally important. Okay, when it comes to obtaining general solutions, of course, because of the nonlinearity inherent in much of these physics, solutions are difficult to compute, and often and typically one needs to go to numerical methods, right? And because of the complexity of the material, and we've seen a good bit of that when we were developing our study of continuum mechanics, because of the complexity of the methods, it's often only by going to numerical methods of solution that the full sophistication of these problems is realized. Okay, if we stick with analytic problems, we are forced to simplify the treatments to the point where important effects are lost, right? And we saw that repeatedly in the context of nonlinear strains. We saw it in the context of notions of frame invariance, isotropy to some extent, also the effects like the pointing effect and so on. Okay. And when one is talking of numerical methods, the most general sort of treatment of these kind of continuum problems is, of course, with the finite element method. Okay, and the nice thing about the finite element method is that it is applicable to everything I've put down on this slide and much more. Okay, and that will be a different series of lectures at a different time. Okay, anyway, I think this is a good point just to end this segment. It's a sort of midway recap of where we are and where we can go, and paying due regard to the people who helped us get here. And so when we come back in the segment following this one, we will start out by looking at briefly at the formulation of thermomechanics, and then we'll follow that up with mass transport.